Hi. Now that I've introduced decision making and looping structures, we can start doing some fairly sophisticated programming. Usually this includes a lot of calculations, which can become very time consuming. So one facet of numerical analysis is to create code that provides results in a reasonable amount of time. For example, in one failure investigation I was involved in, some liquid hydrogen was inadvertently pumped into a warm duct. The hydrogen vaporized very quickly, which created excessive pressures in the duct, causing it to bend. One tool used to investigate the failure was a computer program which predicted the combination of fluid mechanics and heat transfer that caused the surge. I wrote the fluid mechanics part of the program, and that code took about 2 hours to run. The thermal analysis group incorporated the heat transfer into the code. Once they'd added their part, the code took nearly 24 hours to run. The code just became too inefficient to be a useful investigative tool. This video gives a few tips as to what might help or hurt the efficiency of your code. These tips won't be necessary for this class, but may come in handy in the future. The first issue I'll cover is the use of loops versus MATLAB's built-in array operations. Executing looping structures is usually more time-consuming than performing a similar operation using MATLAB array or matrix operators. This is because, in general, looping structures will operate on individual array elements, while MATLAB's array operators work with multiple elements at a time. For example, consider the element-by-element multiplication of two arrays. Suppose I want to create an array C that's the array product of the matrices A and B. I can simply and efficiently use MATLAB's .times operator. This process could be implemented as a set of nested for loops, as shown here. For any combination of n and m, C of m comma n is the product of the elements of A and B at that location. The nested loops just create every possible combination of m and n. The elements in C are created one at a time. MATLAB's built-in array operators are extremely efficient because they perform a process called vectorization. That means that operations are executed using all elements in the arrays at once. This usually results in operations being executed much faster than if they were implemented using for loops. Later versions of MATLAB will attempt to vectorize the loops you create when your code is converted to machine language, a process called compiling. So the difference in efficiency between loops and array operations isn't as drastic as it used to be. Still, array operations will typically execute more quickly than a corresponding looping structure. So, in general, multiplying the two matrices of our previous example can be done faster by using .times to do the multiplication rather than for loops. To reiterate, in this class, I will usually require you to write your own code containing loops which will operate on individual array elements, rather than allowing you to rely on MATLAB's array and matrix operators. This is for educational reasons, and once you get out of this class, feel free to use the built-in operators to your heart's content. You can, of course, always check the results of your looping structures by using MATLAB's built-in operators. There are a couple of other ways to improve efficiency, even if you're writing your own looping structures. One approach is to pre-allocate memory for arrays that you'll be creating in your loops. When you change the size of an existing array, MATLAB has to request additional memory from the computer to accommodate the increased size. So if you're creating an array element by element, every time your loop adds to the size of the array, MATLAB has to take time out from computing and go ask the CPU for more memory. On the other hand, if you know that your loop will create an array with 100 rows and 100 columns, one element at a time, you can use the zeros command to create a 100 by 100 array of zeros before entering the loop. Then the loop will just overwrite existing zero values, but no time needs to be taken out to change the amount of memory required for the array, since all of the necessary memory was allocated when the zeros command was executed. Displaying results of calculations to the computer screen is really time-consuming. So if you're executing looping structures that perform a lot of calculations, suppress the display of the calculation results by following the line with a semicolon. If you want to find out how long a section of code takes to execute, you can use MATLAB's tick and talk commands. Type tick just before the code you want to time, and talk just after that code segment, and MATLAB measures the amount of time between when those commands are encountered and displays that result to the screen when the talk command is encountered. Tick and talk measure the total elapsed time, not just the time MATLAB spends executing code. Operations that your computer is performing in the background can affect how long it takes for the code to execute. So you may find that the results you get from using the tick and talk commands vary from time to time when you run your code. Now I'll show how these approaches look in MATLAB. Here are the equations I'm going to implement. These equations govern the current in an inductor that is subject to a voltage pulse. The details probably aren't important for this application, but the problem is the same as exercise 6.2. You can look that exercise over if you want some context for the problem. Anyway, the current is given by this equation for time from 0 to 1 second, and by this equation from 1 to 3 seconds. I want to calculate the current for time between 0 and 3 seconds at time intervals of 1 microsecond. I'm going to end up calculating 3 million values for current. In the demo for this example, I'll use both looping structures and array operators to evaluate these equations and compare the time required for each approach. Since I'm not really doing anything here that we haven't done before, I've already created a script file named rlresponse.m to implement 3 different approaches to calculating the inductor current. First, I set all the constants and a vector containing times. The first approach I use to calculate the current in this file is to just loop through the time values, check whether the time is less than or greater than 1, and evaluate the appropriate equation for the appropriate time. I've bracketed the set of code with the tick and talk commands, so MATLAB will display the time elapsed while executing the code. The next approach is the same as the previous one, but I use the zeros command to pre-allocate memory for the current values before entering the loop. Again, the tick and talk commands display the elapsed time. Notice that I clear the old values for current before doing this, so that I can get a time estimate that's consistent with the first approach. Finally, I'll use array operations. First, I pre-allocate memory for I. Then I use the find command to determine which equation to apply to the values. The values of current corresponding to times less than or equal to 1 are calculated here. The values of current corresponding to times greater than 1 are calculated here. As usual, the tick and talk commands are used to find out how long this process takes. Now I'll run the code. Pre-allocating the memory reduced the elapsed time to less than 1/3 of the time required with no memory pre-allocation. Using array operations reduced the time by about a factor of 2 from the approach using loops and pre-allocation of memory. Finally, I'll take a look at how much time is required if I display the values of current while they're being calculated. This will have a pretty drastic effect, so I'm going to reduce the number of points calculated by changing the time between points to 2 times 10 to the minus 4. So this time around, I'm going to cut the number of points by about a factor of 200. Now I'll take the semicolons out of the calculation of current in the first method. When I run the code, a bunch of numbers start scrolling past. Let's take a break while this is running because it's going to take a while. Okay, I'm back. It took this long to calculate 200 times fewer values. Input-output is very time-consuming. That ends my introduction to MATLAB and programming structures. Next, I'll finally start talking specifically about numerical analysis and solving engineering-type problems using MATLAB. However, the programming tools I've introduced so far will be used throughout the rest of the course, so you get plenty of practice with creating functions and decision-making and looping structures.